Welcome to Chapter 14 of And So, Squircle. In this video, we'll be deriving the law of sines and cosines when looking at a triangle in the p-norm. To start, let's quickly demonstrate the derivation for the law of sines in the 2-norm. We'll take this arbitrary triangle and drop an altitude with a height h. Something we can show now is that the sine of a is h over b, and the sine of b is h over a. We can solve for h in both equations, and since they're equal, equate the two. This then gives us the familiar law of sines formula for only a and b, but dropping a second altitude anywhere would give us the final part. We're going to try to do something very similar with our p-norm law of sines derivation. The only caveat is that we have to make sure that it's an arbitrary angle with an arbitrary rotation. The reason being that rotations change the length of a triangle in a p-norm. For example, if we take a line with Euclidean length 1 and rotate it about the origin, its forelength is not constant. Because the 4-normed space is more convex than the 2-normed space, its length in the 4-norm decreases as we move away from the axes. That means that we're going to have to take into account the way that our triangle is rotated in the coordinate plane. So of course we'll take our triangle, but then add these angles to the outside, notated with lowercase Greek letters. To find the law of sines, we want to find a common expression for the length of this altitude h, and we'll do that with our vector projection formula from chapter 10. We're going to assume that all lengths on this triangle are their p-normed lengths, so our form for h is going to be the projection of segment AC onto DC, or rather, the orthogonal projection of AC onto AD. This is the same formula as normal, but using sine instead of cosine. I'll flash the proof for orthogonal projection on the screen real quick, because the reasoning behind this formula is very intuitive, and I don't think it's necessary to dedicate a section to it. But now, using the orthogonal projection formula, we can find an expression for h on the left triangle. For the triangle on the right side, we have to slightly change our perspective in order to figure out what angles we need for the projection formula. To make it easier to see, we'll move the origin along this line from A to B. Due to the properties of the metric and p-normed spaces, this keeps the triangle's length the same while letting us look at the angles in a different way. We'll extend alpha over here and use the orthogonal projection formula for h again. This time, seeing the segment BD as being drawn at an angle of alpha plus pi, and the segment BC at alpha plus pi minus b. Using Hipes periodicity for pi over 2, we can simplify this expression. Now we'll set the two h's equal to each other, and through some simplification, we reach this form. Now we can do this with different altitudes and starting from different perspectives, and what we'll end up with is 3 different expressions for the law of sines. You can tell that there's a pattern here, so we could write this expression this way instead, where the n's and n's correspond to the correct language in case and the index is modular, so if n sub I is c, then n sub I plus 1 is a. But going back to the 3 cases above, what if we tried to combine those equations? Let's solve for sine a over a. We'll end up getting this 3-way equality, which is very close to the law of sines we're used to. I'll divide by hype of alpha minus b, and here is something that we want to notice about these hype terms. Hype of alpha minus b is actually equal to hype of gamma plus c. They cancel each other out. If we go back to the diagram of the triangle and zoom in over here, we can show this hype equality fairly easily. So first, we have alpha plus pi, and then going back by b. That lands us on the line A. We'll also get there if we take the path pi over 2 plus beta. And finally, if we look upwards, we can do the angle pi, then add gamma and c, and subtract pi from that to reach the ray that side length A lies on. Now with all of these angles being equal to each other, then their hypes are equal to each other as well. This pattern can be repeated for all sides of the triangle, resulting in this general statement being true. Dare I call this the law of hypes? I don't see why not. But anyway, we can use the law of hypes to definitively show that this statement can simplify to this. If we take a closer look at the expression though, notating the side length of the p-norm and looking at the triangle again, it's easier to see that this p-normed law of sines is just an expanded Euclidean law of sines. And the same is true for the law of cosines. The new version is a bit long to fit on screen, but I'm sure you get the idea. So I suppose the most interesting thing that we end up getting from this exploration is this law of heights, and I guess the formula for the magnitude of an orthogonal projection. Sigh. Okay, bye.